My name is Keaton Strongman. I'm a PhD student at Laurentian University, and I'm on the Geraldton-Onaman, or Beardmore-Geraldton, depending on who you ask, transect. And what I'm studying is the metallogeny of that transect, so trying to understand what makes that transect so substantially different from areas like the Abitibi. And what I'm presenting today is really a summary of my final paper of my PhD, which is hopefully coming to a paper near you soon. So keep your eye out on that, and hopefully Harold doesn't give me too many edits there. No pressure. So what I'm going to talk today about is the influence of Mesoarchean crust, and this has kind of been a central theme of this workshop on metallogeny and geodynamics. And I think this is really one of the key things that we've started to identify in controlling metallogeny at this scale. So I always have to pump this a little bit. This is really the central problem of Metal Earth, and that's that Archean greenstone belts have variable metal endowment. And what's really interesting about this is that this variable metal endowment is present at different scales. But what's crucial is that it's present at the belt scale, right? We see a difference at the belt scale, and we see a difference at the assemblage scale. And what this means is that we're looking for either a process or a feature that is at the belt and or assemblage scale that can explain that difference, right? So you're looking at a commensurate process or feature to explain that difference at a similar scale. So I always like to throw this in a little bit because I think what's really interesting with Metal Earth is that we've actually started to go into the less endowed greenstone belts. The less endowed greenstone belts just don't get a lot of love, and I think that's really because it's tough to get money to go in and do research in these areas. Companies, if they don't have deposits in the area, they don't really want you to go in and look. So this is an opportunity with Metal Earth to look at these areas that are quote-unquote less endowed and kind of close the loop, because often what happens is we go into a well-endowed greenstone belt, we identify all the features associated with mineralization, and we go, great, we've solved it, and then we never actually test the null hypothesis that those features are present in less endowed greenstone belts. So this is a huge hole in mineral exploration research, and it's something that I think we've really had an opportunity with Metal Earth to help to solve. And I'm going to pump the Onaman-Tashota greenstone belt here because I think it's the perfect candidate for a less endowed belt, mainly because it has no producing or historical base metal mines. So not exactly ideal if you invested in a company there, I'm sorry for that, but certainly important for us when we consider endowment. And it only has limited production of gold from historical occurrences, which are very small. We're talking, the largest one being around 100,000 ounces of gold, which is really not even a deposit nowadays. So what we need to ask ourselves are, what are the fundamental differences at the belt scale and at the assemblage scale between this sadly less endowed belt and the more endowed belts like the Abitibi that we've been looking at? And, oops. There we go. So we can lay out some broad scale differences just by looking at a map right away. And we've just seen some maps of the Abitibi, which is helpful. So hopefully you can keep those in your head here. But the first thing that stands out right away is that we just have a smaller volume of volcanic rocks, both in absolute sense, there's just less volcanic rocks. The belt is smaller, and in a relative sense, relative to plutonic rocks. So there's a lot more plutonic rocks. This is the Onaman-Tashota greenstone belt here. You'll notice the size of these gneissic and intrusive complexes is massive when you compare it with the volcanic material. So this is a really obvious difference at the belt scale that we can identify right away. Another thing that stands out, and you look at the color scheme here on this map, is that we have a much greater abundance of felsic and intermediate volcanic rocks. These things are typically, less than 5% in areas like the Abitibi. And here, they can be upwards of 30-40%. And this is a big difference, and it's something that we can identify right away without spending a lot of money. So companies can look at differences like this, they can identify them right away, and can make decisions on greenstone belts. And that's really something that's important for the research that we're doing, is to be able to apply this in the industry easily without, using complicated and difficult methods that the average geologist just doesn't understand. Another thing, and it's kind of difficult to show this, but is that there are no ultramafic rocks in this greenstone belt. Really, the only thing I can say to prove this is that it's not in the legend that I made here, so you just have to believe me. But there are no ultramafic rocks, with the exception of a few layered mafic intrusions, within this greenstone belt. And that's a really big difference because those indicate differences in processes. When we plot all of the chemistry of this greenstone belt, this is just a plot taking all of the felsic rocks of the belt and just quickly dumping it in and seeing where it plots. You'll notice that we have this dominance of F1 signatures here on the Hart et al. Diagram, and only a few F2 rhyolites. And noticeably absent are any F3 rhyolites. So this is a big difference. And again, this is something that's easy to do. Companies can easily collect whole major element data and trace element data like this from whole rock samples, plot these up, and this is an obvious difference that stands out right away. And it really indicates a lack of shallow melt rhyolites, rhyolites generated in a shallow crustal setting. And again, this all comes back to this idea of thicker crust, pre-existing Mesoarchean crust. You've seen this diagram now a few times, so I won't spend too much time on it, but what's really critical about this, and it stands out even when you look at the Wabigoon here, this is the entire Wabigoon, here's the eastern Wabigoon over here blown up, and you'll notice that we really don't have very much juvenile material, any sort of juvenile neodymium model ages. And there's hafnium data in here as well, some sparse hafnium data from zircons, and it shows the similar pattern. We just don't have juvenile material in this greenstone belt. Nearly all of it is contaminated. And finally, we actually do have a wide age span of volcanism. So this is just sort of hammering these together into rough informal episodes. But what you can see, and you don't need to pay attention too much to the detail, but what I want you to notice is the time scale here. We have inherited zircons in the Paleoarchean. We've got several episodes in the Mesoarchean, and then we've got 2 separate episodes in the Neoarchean. So this is a wide age span of volcanism, prolonged crustal development over a long period of time. And this is very different from an area like the Eastern Abitibi, in which most of the rocks are formed in a very short period of time. So this is an older interpretation of one of our seismic transects. And really, what I'm trying to show you on here is a difference in these 2 greenstone belts. So here's the Beardmore-Geraldton greenstone belt right there. And then from here upwards is the Onaman-Tashota belt. And the Beardmore-Geraldton greenstone belt is arguably a decently endowed. I would call it moderately endowed. It has one world-class gold deposit, but the belt itself is quite small. And when we look at things like structural connectivity, we can see much better defined structures within this greenstone belt. We see thin areas of interpreted upper crust. And when we look at the Onaman-Tashota belt, we do not see nice through-going structures that we can connect through this belt. And we see a thicker upper crustal sequence. So these are obvious differences between 2 belts which are juxtaposed with one another. And so that was a bit of a long-winded intro, but I was all trying to get to here, and that's the central hypothesis of this paper and really of my thesis, and that's that the Mesoarchean crust strongly influences the geodynamics of Neoarchean assemblages, and that happens because it changes the volcanic stratigraphy, it changes the volcanism, the style of volcanism, and that all feeds in to create differences in metallogeny. And it's not just a difference in endowment, it's a difference in metallogenic sequence. You do not have the same style of deposits. You actually have different deposits within this greenstone belt. And that has really confused companies trying to do exploration in this area. And so we're going to look at 2 examples here from either end of the belt. We're going to look at the southern margin of the belt, and we're going to look at the northern margin of the belt. We're going to try to deconstruct the metallogeny in brief as quickly as I can here before everybody falls asleep. So we'll start out with the southern package, and this is known as the Elmhurst-Rickaby assemblage. It's 2740 to 2734. This is the greenstone belt here again, and then this is just a blow-up of this area here, and you can see the assemblage down here. And what's really interesting about the Elmhurst-Rickaby is that it's actually one of the largest andesitic packages within the Archean that is truly andesitic and not just a slightly fractionated basalt. That's cheating. These things are real andesites. And the entire package, including the basaltic rocks, is calc-alkaline in nature. And we believe it's co-magmatic based on the trace element data that we've got. And the last and probably most important thing from my perspective is that this area hosts a whole series of base and precious metal occurrences, and I call them atypical here. What I'm really just trying to say is that they're not regular VMS, and hopefully I'll be able to show you that. So this is the interpreted stratigraphy in a simplified diagram. You don't need to worry about reading all of this. We're going to break down some of the key units. But essentially what we're trying to do is build a stratigraphic sequence and look at the change in volcanism through time and then place mineralization into this context. So we'll start out with the base of the assemblage. This is the Castlewood Formation, and it's a mafic flow-dominated sequence. On the surface, it might look quite simple, but when you start to pick it apart, you see quite a bit going on in here. We've got several volcaniclastic members that are intermediate in nature. They've got things like silicified juvenile fragments in them that are very interesting. But what's really interesting about this package is that it's entirely calc-alkaline in nature, and it becomes progressively more andesitic as you move up through stratigraphy. And we have things like feldspar phenocrysts, amphibole phenocrysts that have gone to chlorite starting to pop up. And this is really interesting. It's not what you typically see in a volcanic succession. We take a look, we don't really have time to go through all the physical volcanic features, but one of the key ones is that in this area we do see hyaloclastite in between the pillows. So here's some highly transposed pillows here, and you can see hyaloclastite in between if you're standing close to the screen. And what this indicates, of course, is subaqueous volcanism. So this was deposited in a subaqueous setting. And in general, these sorts of packages are interpreted to be mafic shield-style volcanoes, right? So that's likely what we're looking at in this setting. If we look at the overlying assemblage, or overlying formation, that's the Rickaby Formation, and it's much more complicated and much more atypical. It essentially forms a complex pile of andesitic and dacitic volcanic rocks, and again, we have fractionation from the bottom to the top of the sequence. So when you look at this stratigraphic column here, one thing stands out right away, and that's this dominance of coarse volcaniclastic material. It's actually the main rock type in this area. It's dominant over much more subordinate flows and intrusions. And what's really interesting, Harold may disagree with this, but what's really interesting is we move to the top of the sequence, we see interesting things with some of these dacites up here in the Kenty member. And they essentially have what we think are spine-like structures. So these are areas where we have flow banding terminating at basically 90 degrees to the flow top contact. And that's not exclusive to subaerial rhyolites and dacites, but it's certainly something that we typically see in subaerial rhyolites and dacites, and something that's not all that common in subaqueous units. We also don't see any hyaloclastite in the flow top breccias of these units, despite excellent preservation. So this is not definitively subaerial, but it's certainly what we would expect if we were looking at subaerial rhyolites. And overlying this, we have a series of intermediate tuff breccia units that have sub-rounded fragments, and you can see some examples of that here. And what this is really reflecting is subaerial exposure of the volcanic edifice and erosion. You need to erode these fragments to round them. Typically, mass flows in volcaniclastic deposits do not generate a lot of rounding of fragments, particularly of fragments like this. And so what we think we're looking at here is essentially a constructive volcanic edifice which is recording subaerial emergence near the end of its age. And so this is where we're going to get a little controversial here, but this is typically what you would see in a stratovolcano-like sequence. You would see a complex pile of volcaniclastic material interlayered with flows and riddled with intrusions, and possibly the evidence for exposure of that sequence above the seafloor towards the end of its evolution. So we'll dive into the petrochemistry a little bit because it's particularly interesting. If you take a look at the trace elements here plotted on this Pierce diagram that's modified from Winchester and Floyd, one thing that you see is right away this is very different from an average greenstone belt, which usually shows a bimodal distribution of mafic rocks down here somewhere and then felsic rocks plotting typically up here as a cluster. Instead, we see a near complete fractionation trend or assimilation trend from mafic rocks down here all the way up to the felsic rocks at the top of the stratigraphy of this assemblage. So this is consistent with fractional crystallization, and we do have lots of phenocrysts in this assemblage which would indicate fractional crystallization, but there are other ways to generate this kind of pattern. If we look at the spider diagrams, we see some very interesting things. So what I've done is plot the mafic rocks at the base of stratigraphy up here, the intermediate rocks, and then the felsic rocks. And you might ask, well, why didn't I plot these all on one plot? And that's because they plot right on top of each other. So this is a bit strange. We think this is a comagmatic suite because they have relatively consistent profiles, although the anomalies are more pronounced. And yet we have continuous abundance of trace elements instead of seeing the intermediate rocks plot up here and the felsic rocks plot above. And what this likely indicates is that you must have juvenile melt input as you're fractionating this sequence or as you are assimilating rock. Otherwise, you would expect this to fractionate up to higher values. It also likely indicates a metasomatized mantle source, or at least melting with rutile involved, so that you can get these niobium and titanium anomalies. And finally, when we plot on, I'm not a massive fan of these diagrams, but they can be really helpful to show processes as opposed to fingerprinting. A lot of people misuse these and just use them to fingerprint an area, but if you really break these down, what these diagrams are very good at doing is showing you processes. And so what we see here is essentially a straight upwards data trend off of this Morb OIB array. And what that reflects is decoupling of thorium and niobium. And so that can be done through assimilation of Archean crustal material. And I've plotted average Archean crust up here, and you can see that lines up. But we also see a trend that's roughly parallel to the array, and that typically reflects fractionation. And so what we're looking at here is a combination of fractionation and assimilation. So what about the mineralization? Well, I think there's enough VMS buffs in the room. Harold and Mark are over there. They can probably confirm that this does not look like your typical VMS setting. So this is just one example of some of this strange mineralization within this greenstone belt. This is a property called the Ishkade, and what they've got there are these comb-textured quartz vein networks. And you can see on the left here this massive network of veins. It reaches up to about 40% vein density, so incredibly rich in vein material. And when you cut these veins open, what you see are beautiful comb textures, preserved despite the fact that these rocks are 27, 40 million years in age. So that's really, really actually pretty cool. And it's associated with base metals and low grades of gold. But even more strange, when we look at the alteration, what we see is actinolite magnetite, titanite, all kinds of weird phases in there. And that's really calc-sodic alteration. That's not typical of an epithermal system. It's actually the kind of thing you would find at the base and flank of a porphyry deposit. You can sometimes find them associated with IOCG deposits. And so this is really a strange association of textures and alteration mineralogy, particularly because this kind of mineral assemblage is typically stable over about 500 degrees Celsius. So this is really, really hot to be in something like the epithermal realm, and yet we have comb textures, which indicates extensional features. So this is a really interesting and different deposit. And so it's really, without breaking down exactly what it is, it's got a lot of features that fit within this porphyry epithermal spectrum. And there are other occurrences that I don't really have time to go over in this area that have similar features. So, is Phil asleep yet? Phil, go to sleep. Don't pay attention to this part. Let's discuss the geodynamic model here. Now, I'm not usually a giant fan of the horizontal tectonics models in the Archean because I think they often fail to explain a lot of the key features. And yet, when you put all this together, the volcanic facies associations, the petrochemistry of the rocks, the mineralization styles that we have in this part of the belt, really, it all adds up to what you would expect in a Benioff-style subduction zone in an arc. We have mafic shield volcanism followed by a constructive volcanic edifice, extensive fractionation and assimilation, so AFC processes. And what this really indicates is that the crust is likely in compression. It's either thick and or it's in compression because you need to store melts in the crust in order to make these kinds of rocks. Okay, and that just doesn't happen in rifting scenarios for the most part. And that's partly why I've drawn this on here like this. And what's really interesting about this is I think this actually sort of argues against subduction in the majority of Archean scenarios, because a lot of the argument is that, well, in Archean scenarios, we might have had subduction, but it just didn't make andesites for whatever reason. Well, sometimes it does. And here we've got a good example of that. And something I'd like to talk about a bit as well is that you can use mineralization as a bit of a proxy for environment as well, right? Certain mineralization forms in certain environments, and these styles of mineralization form in this style of environment. So what about the effect of the Mesoarchean? How might this have influenced this development, this geodynamic development, this geodynamic evolution and the mineral systems in the area. Well, if you have stable TTG-rich crust, this is critical in allowing you to generate something like a subduction zone. A common issue in Archean models is that it's difficult to make subduction initiate because we don't have the density contrast needed to make a subduction zone. Well, here you would, because you've got much older crust sitting below, and that's going to allow you to develop the kind of density contrast that you might need. A thick crust will also prevent melt ascension, especially if the crust itself is in compression, and this will promote melt storage, and this is what allows you to create these kinds of sequences of rocks, andesites like this. And so what we end up with is at least a petrogenetically similar setting to an arc. Whether or not it was truly geodynamically similar to an arc, it remains to be seen, but certainly the petrogenesis of this is similar to that in an arc sequence, and we have an arc-like metallogeny in this part of the greenstone belt. So let's look at the northern end of the greenstone belt and see what we see up there. And that's defined by this Marshall Lake assemblage. Here's the greenstone belt again. Marshall Lake is this massive felsic package near the northern margin. And it's roughly speaking 2734 to about 2739. The ages of it are not extremely well constrained. And again, it's the northern margin of the belt. Unfortunately for us, it's in structural contact with all of the other assemblages of the belt, or an intrusive contact. So we don't have a really good idea of how this relates to the other assemblages. But what's really interesting is that it's comprised entirely of felsic volcaniclastic material and flows with basically no mafic magmatism going on while this is deposited. All we have are sparse and very sparse mafic dikes associated with this. And that's very atypical. Typically you have bimodal volcanism. You don't usually have a massive outpouring of felsic rocks with no mafic rocks at the same time. And when we look at the chemistry of this, the entire package is F1 in nature. And we'll see some strange VMS-like mineralization in it as well. So again, here's the stratigraphy. We don't need to pay too much attention to it. We'll walk through some of the key units here. So the base of stratigraphy is defined by the Grip Lake, Camp, and Marshall Creek formations. It's dominated by felsic tuff and lapilli tuff. And what's really interesting about it is that it's loaded with what we think are juvenile fragments. So these are essentially wispy fragments with sub-rounded margins and amoeboidal textures that really look like volcanic glass material, possibly pumiceous material that has been flattened out. It's also intruded by synvolcanic dikes and sills, with a few felsic flows interlayered. And so this is generally indicative of explosive pyroclastic volcanism. Now, it's very controversial to argue for a caldera in any area. You need a lot of evidence, so I'm not going to do that here, but what I will say is that it has a lot of the features that you typically find in a caldera, especially in the early sequences of a caldera where you have a lot of pyroclastic material. The overlying assemblages, or overlying formations rather, are the Deeds Island and Eagle Island formations, and these are dominated instead by flows and domes with only minor volcaniclastic material. And what's interesting is that there's hyaloclastite within these flow-top breccias. I forgot to mention that there's hyaloclastite in the flow-top breccias of the lower formations as well. And so this indicates that the entire assemblage was deposited subaqueously, despite the fact that there's quite a bit of volcanic material here. So we need a lot of synvolcanic subsidence, and that also might indicate a caldera-like setting, although again, it's very difficult to definitively prove that. Juvenile material is much less prevalent in this part of this assemblage, and so this might indicate something like volatile depleted felsic volcanism, and again, that's the kind of thing that you can sometimes find during caldera resurgence and rim collapse. So that's possibly the kind of setting that we might be in here. So looking at the petrochemistry, this is very interesting. I meant to change this to unimodal, just to ruffle some feathers, but essentially what we have here is unimodal felsic volcanism. This is a similar plot, a Pierce plot here, and we can see that we just have one cluster of samples here, all within essentially one area. No associated mafic igneous activity, with the exception of a few dikes that appear to be late. When we look at the affinity, it's entirely calc-alkaline, F1 in nature, so this likely indicates hydrous melting of a mafic source. And again, that melting needs to have happened deep within the crust because we are in the garnet stability field. So let's take a look at the mineralization in this area. It's a little bit atypical. It's essentially volcanogenic massive sulfide-like systems. So we have lenses of pyrite and chalcopyrite with stringers. You can actually see a lens right here plunging in towards the screen, and those of you who are close to the screen can see the sulfide burn coming off of it, and that's the stringer zone leading right up into it. So we have VMS-like morphology, and yet when we look at the alteration, what we see are aluminosilicate-bearing assemblages. And so this can represent really acidic alteration, things like advanced argillic alteration. And if you take a look at the photomicrograph on the right, what you can see is blasts of kyanite within a quartz ground mass. And note that there's really no other minerals there. That's kyanite and quartz. So the only elements that are left in this rock are aluminum and silica. Right? So this is really, really atypical for traditional VMS, which would have chlorite and sericite alteration. And so what we might be seeing here is a system in which you either had a lot of boiling or magmatic volatile input, or possibly a combination to generate these kinds of really acidic alteration assemblages. And so taking it back to a geodynamic model, it's certainly in a caldera-like volcanic setting. Whether or not it's a true caldera or not remains to be seen, but it's a caldera-like setting, and it's indicative of very immature crustal rifting. So we are just basically rifting the crust enough to emplace felsic melts here. We need to melt a hydrous source at about 30 kilometers or more depth, and that's allowing us to generate VMS systems with argillic and advanced argillic alteration. And so this one is very easy to see what the effects of the Mesoarchean crust might be. If you take a look at this diagram here, I've plotted some of the basement ages based on isotopes. So we've got very old basement material up to 3.5 model ages and 3.1 model ages on the other side. And it's quite conceivable that that was the material that was melted to generate the felsic rocks within this package. And so thick, stable crust would possibly inhibit extensive rifting, or potentially we just didn't have extensive rifting, and that's why we still have thick, stable crust here. But this would certainly favor a deep melt source for the rhyolites, and a thick, stable crust provides a density filter. So this promotes underplating. If you have TTG-rich crust, then mafic melts do not have the buoyancy necessarily to ascend to the surface in these kinds of settings, and may pond at the base of the crust, melt the crust, and that might be what generated these kinds of assemblages. If you're melting hydrous mafic crust, that is what's going to allow you to generate these calc-alkaline signatures. And it turns out that calc-alkaline F1 volcanic rocks are water-rich and typically are slightly oxidized. And so if you want to make magmatic volatiles and you want to input them into something like a VMS system, this is a good way to do it, is to have a whole bunch of F1 rhyolites in the area. And so we have acidic VMS deposits associated with these F1 rhyolites. And so coming back to the hypothesis that I sort of put out at the beginning of this talk, and that's that Mesoarchean crust influences the geodynamics of Neoarchean assemblages. I think we can see from these two examples that we see a very different sequence of volcanic rocks, a difference in petrogenesis, and a difference in metallogeny that results from this within the Neoarchean rocks. And this is quite possibly explaining why we have so much less endowment within this greenstone belt. You're just not developing high-level heat flow hydrothermal systems to make your big VMS. Instead, you're making these kinds of odd hybrid-like deposits, porphyry epithermal-like deposits that just aren't quite making it in terms of mineral endowment. And that's it for me. Thanks.